Picture this. A burst of radio waves shoots across the cosmos, packing more energy than the Sun emits in 80 years, and then it vanishes in less than a blink of an eye. No warning, no explanation, just a cosmic flash so powerful it outshines entire galaxies. This isn't science fiction. These are fast radio bursts, one of space's most puzzling secrets. For nearly 2 decades, these mysterious signals from deep space have left scientists scratching their heads. Some come once and disappear forever. Others repeat like clockwork. Some seem to carry hidden patterns, and a few have traveled halfway across the observable universe just to reach us. Today we're diving into 25 mind-blowing mysteries surrounding fast radio bursts. From their mind-bending energy to theories about their true origins, including the wild possibility that we might not be alone in the universe. By the end of this video, you'll understand why these fleeting cosmic flashes have become one of astronomy's greatest enigmas. So buckle up, we're about to explore the unexplained. Now, let's tackle the first and perhaps most baffling mystery of all. Where do these fast radio bursts even come from? Imagine trying to find a needle in a cosmic haystack, except the needle flickers for just milliseconds, and the haystack spans billions of light years. That's the challenge scientists face when hunting for the origins of FRBs. The leading theory points to magnetar neutron stars with magnetic fields so intense they could strip the information off a credit card from halfway across the Milky Way. These cosmic powerhouses occasionally unleash colossal flares, and some researchers believe FRBs might be their way of screaming into the void. In fact, in 2020, astronomers caught a magnetar in our own galaxy belting out an FRB-like signal, adding weight to this idea. But here's the twist: not all FRBs match magnetar behavior, leaving room for other suspects. Then there are neutron star collisions. Picture 2 ultra-dense stellar corpses slamming together, releasing enough energy to outshine a supernova. These violent mergers could theoretically produce FRBs, but the timing doesn't always add up. Many bursts seem too frequent or too isolated to fit this model neatly. Black holes, the universe's ultimate enigmas, also make the suspect list. Some theories suggest FRBs could be the death cries of matter falling into them, or even echoes from black holes interacting with surrounding plasma. Yet, no smoking gun ties black holes directly to these bursts, and yes, we have to address the elephant in the cosmos. Could FRBs be signals from extraterrestrial civilizations? While it's a tantalizing thought, the sheer energy required makes it unlikely. An alien transmitter would need to harness the power of a star just to send a millisecond hello across the universe. Most scientists agree nature is the more plausible culprit, but the debate keeps the mystery alive. The real headache pinpointing where these bursts originate. Most FRBs arrive from galaxies so distant their light has traveled for billions of years. By the time we detect them, their birthplaces might not even exist anymore. It's like hearing an echo from a mountain that eroded eons ago. So while we've narrowed down some suspects, the origin of FRBs remains a cosmic whodunit, one that keeps astronomers staring at the skies, waiting for the next clue to crack the case. Moving from the cosmic whodunit of FRB origins, let's unravel another layer of this mystery: why some of these bursts repeat while others vanish without a trace. Imagine a cosmic strobe light flickering unpredictably, sometimes flashing just once and other times pulsing in a pattern we can't quite decipher. That's the puzzle of repeating versus non-repeating FRBs, and it's forcing scientists to rethink everything they thought they knew about these enigmatic signals. Take FRB 121102, the first repeater ever discovered. Unlike one-off bursts that disappear as quickly as they arrive, this one has been sending signals our way since 2012, like a cosmic heartbeat. It's localized to a tiny, star-forming dwarf galaxy 3 billion light-years away. and its persistence suggests something wildly different is at play compared to single bursts. Some theories propose it's tied to a young magnetar, possibly born from a supernova, whose furious magnetic energy fuels these recurring eruptions. But here's the kicker: most repeating FRBs don't follow a strict schedule. They're sporadic, sometimes going silent for months before firing off again, as if whatever's producing them has an unpredictable power switch. Now contrast that with non-repeating FRBs. These are the cosmic one-hit wonders, blasting onto the scene with a single, brilliant flash before fading into oblivion. Their fleeting nature hints at catastrophic, one-time events like a neutron star collapsing into a black hole or a collision so violent it leaves no survivors. But even that explanation isn't airtight. Why? Because some regions of space seem to produce both repeaters and one-offs, suggesting the same environment could spawn wildly different behaviors. It's like finding two volcanoes side by side, one erupting constantly and the other going silent after a single explosion. The difference between repeaters and non-repeaters might come down to the engines powering them. Repeaters could be fed by long-lasting energy sources, like a magnetar's enduring magnetic field, while one-offs might stem from short-lived self-destructive events. But there's a twist. Some initially silent FRB sources have suddenly started repeating years later, as if they were dormant and suddenly woke up. This has led to wild speculation. Could some non-repeaters just be repeaters on a cosmic coffee break? What's clear is that this duality is more than a quirk. It's a clue. If all FRBs came from the same phenomenon, we'd expect consistent behavior. The fact that they don't implies multiple origins or, at the very least, multiple ways a single source can behave. It's a reminder that the universe loves variety, and FRBs are no exception. So the next time you hear about a new burst, ask yourself, is this a cosmic shout into the void or just the first note in a longer, stranger song? Now let's shift our focus to something truly mind-bending: the sheer power packed into these fleeting cosmic signals. Fast radio bursts don't just whisper across the universe, they scream. In mere milliseconds, a single FRB can unleash more energy than the sun radiates over tens of thousands of years. Wrap your head around that for a second. An event lasting less than the blink of an eye outshines our star's steady glow for generations. That's like a firecracker outmatching a bonfire, and it's precisely why scientists are both fascinated and baffled. So how does something so brief produce such colossal energy? The leading theories point to extreme cosmic objects with unimaginable forces at work. Take magnetars, for example, neutron stars with magnetic fields up to 1,000 trillion times stronger than Earth. When these magnetic monsters undergo starquakes or experience sudden magnetic field rearrangements, they could theoretically generate bursts powerful enough to match what we observe in FRBs. Picture twisting a rubber band until it snaps, releasing pent-up energy in a violent instant. Magnetars might be doing something similar on a cosmic scale, with magnetic energy instead of elastic potential. But here's where the physics gets messy. Even magnetars, as extreme as they are, struggle to explain the most energetic FRBs we've detected. Some bursts are so powerful that they'd require nearly all of a magnetar's magnetic energy to be converted into radio waves in one go, a scenario that defies our current understanding of how these objects behave. It's like trying to power a city for a year with a single lightning bolt. Possible, maybe plausible, that's the debate. Another puzzle is the efficiency of energy conversion. In most cosmic explosions, like supernova, energy gets dispersed across multiple wavelengths: light, heat, X-rays. Yet FRBs channel an almost unfathomable amount of energy into a narrow band of radio waves with bizarre precision. It's as if nature built a cosmic laser, focusing an entire star's worth of power into a fleeting radio squeal. Current models can't fully account for this, leaving researchers to wonder if entirely new physics, perhaps involving quantum effects or even more exotic objects like cosmic strings, might be at play. And then there's the delivery mechanism. Even if you have enough energy, how does it traverse billions of light years without scattering into noise? Some FRBs arrive crisp and clear, suggesting their sources are embedded in environments with unique properties, like ultra-dense plasma clouds or regions threaded with powerful magnetic fields. These conditions might act as cosmic amplifiers or lenses, preserving the signal's intensity over mind-boggling distances. But again, this is speculation. The truth is, we're still grappling with basic questions. What makes FRBs even more intriguing is their apparent lack of leftovers. Most high-energy cosmic events, like supernova or gamma-ray bursts, leave behind visible wreckage, expanding gas clouds, or lingering radiation. Yet many FRBs give no such clues. They flash, fade, and leave us staring at empty space, as if the universe played a prank with no fingerprints. This absence of afterglow or debris challenges the very frameworks we use to study cosmic explosions, pushing astrophysicists to rethink what's possible in the extremes of space. So while we've made strides in detecting and cataloging these bursts, the energy puzzle remains wide open. Are FRBs the death cries of unknown celestial objects? The byproducts of phenomena we haven't even imagined yet. Every new detection adds another piece to the puzzle, but the full picture is still a blur. One thing's certain, whatever's generating these bursts holds the key to unlocking some of the universe's best-kept secrets, and that's a mystery worth chasing. Now, let's stretch our imaginations even further beyond the raw power of fast radio bursts and into the vast distances they travel. These fleeting signals aren't just cosmic fireworks, they're interstellar messengers carrying clues about the fabric of the universe itself. Detected from billions of light-years away, FRBs act like lighthouses in the cosmic dark, illuminating not just their origins but the invisible material strewn across the cosmos. Picture this: a fast radio burst erupts in a distant galaxy, racing through space for billions of years before reaching our telescopes. Along the way, it doesn't travel through empty space. It slices through clouds of gas, dust, and ionized particles, each leaving a tiny fingerprint on the signal. This is where FRBs become more than just mysteries. They transform into tools. Scientists can measure how the burst's radio waves disperse, how the higher frequencies arrive slightly earlier than the lower ones, to map the density of matter it encountered. It's like listening to an echo to gauge the size of a room, but on a universe-spanning scale. Here's where things get even more fascinating. For decades, astronomers have puzzled over the universe's missing matter, the ordinary atoms and particles that should exist based on our calculations but remain undetected. Traditional methods, like observing visible light or X-rays, only account for about half of this expected matter. But FRBs might hold the key. By analyzing how their signals disperse, researchers can tally up the electrons in the ionized gas between galaxies, effectively weighing the invisible material that's eluded detection. In essence, FRBs are cosmic scales, measuring what our eyes and telescopes can't see. Take FRB 180924, detected in 2016. Its journey from a galaxy over 3 billion light-years away left a dispersion signature so precise it revealed pockets of tenuous gas in the cosmic web, the filamentary structure connecting galaxies. Without FRBs, these regions would remain hidden, too faint and diffuse to spot directly. It's like using a flashlight to trace the outline of a foggy window. Suddenly, the unseen becomes visible. But the story doesn't end there. Some FRBs exhibit far more dispersion than expected, hinting at environments thick with plasma or magnetic fields near their sources. Others, like FRB 190520, show persistent radio emissions between bursts, suggesting they're embedded in dense, turbulent regions. These quirks don't just help us map the universe, they force us to rethink how extreme environments shape the signals we detect. What's truly remarkable is how FRBs bridge scales. A burst lasting milliseconds illuminates structures spanning millions of light years, connecting the physics of distant galaxies to the voids in between. They're not just flashes in the dark, they're probes revealing the universe's skeleton in ways no other phenomenon can. And with each new detection, we're not just solving the puzzle of FRBs, we're piecing together the hidden architecture of everything around us. So the next time you hear about a fast radio burst, remember, it's more than a fleeting mystery. It's a beacon guiding us through the universe's darkest corners and shining a light on the secrets we've yet to uncover. Now, let's rewind the cosmic clock to a moment that changed everything the day astronomers first stumbled upon a fast radio burst without even realizing it. The year was 2007, and a team led by Duncan Lorimer was sifting through old data from Australia's Parkes radio telescope, searching for faint pulsar signals buried in the noise. What they found, though, was anything but ordinary. Tucked away in observations from 2001, there it was, a single, blazing burst of radio waves lasting just 5 milliseconds. At first, the signal was dismissed as a glitch. After all, telescopes pick up interference all the time. Satellites, aircraft, even microwave ovens can create false signals. But this one was different. It came from deep space, far beyond our galaxy, and packed the energy of 500 million suns into that fleeting blip. The team named it the Lorimer burst, and it sparked a quiet revolution. Here's why this discovery was so groundbreaking. Before 2007, no one even knew fast radio bursts existed. The idea that the universe could produce such intense, millisecond flashes of radio energy wasn't on anyone's radar, literally or figuratively. Even Lorimer himself initially hesitated, wondering if the signal was too extraordinary to be real. But the data didn't lie. The burst's dispersion measure, the telltale smearing of its frequencies, proved it had traveled through intergalactic space, making it the first cosmic radio transient of its kind ever detected. The skepticism didn't vanish overnight. For years, some astronomers argued it might be a local anomaly or an unaccounted-for artifact. That changed when more FRBs were discovered, confirming Lorimer's burst wasn't a fluke but a window into a new astrophysical phenomenon. Suddenly, astronomers realized they'd been missing an entire class of cosmic events, ones that could rewrite textbooks. What's fascinating is how humble this discovery's beginnings were. The Lorimer burst wasn't spotted in real time. It was hiding in decades-old data, waiting for someone to connect the dots. It's a reminder that sometimes the universe's biggest secrets aren't found by looking where we expect, but by re-examining what we've already seen with fresh eyes. Today, the Lorimer burst is celebrated as the Rosetta Stone of FRB science. It proved that the cosmos is far more dynamic and far stranger than we imagined. And it all started with a 5-millisecond signal that almost got written off as background noise. Just think how many other cosmic mysteries might still be lurking in old data, waiting for their moment to be discovered. Now, let's fast forward to another game-changing moment in the FRB saga, one that turned everything we thought we knew about these cosmic flashes upside down. In 2012, astronomers detected something unprecedented, a fast radio burst that didn't just vanish into the void. This one came back for an encore. Meet FRB 121102, the first repeating fast radio burst ever discovered, and the signal that forced scientists to tear up their old playbooks. Before this, the prevailing wisdom was that FRBs were one-off explosions, cataclysmic events like neutron star collisions or black hole eruptions that left nothing behind. But FRB 121102 shattered that assumption with a series of bursts, sometimes days or weeks apart, all originating from the same patch of sky. It wasn't a cosmic accident, it was a persistent phenomenon with a story to tell. The real breakthrough came in 2017, when scientists managed to pin down its location to a tiny, turbulent dwarf galaxy 3 billion light-years away. That was a eureka moment. For the first time, we had a cosmic address for an FRB, and it wasn't what anyone expected. This galaxy was small, young, and bustling with star formation, a far cry from the quiet, ancient corners of space where such energetic events were thought to unfold. The discovery hinted that FRBs might be tied to environments where massive stars are born and die in dramatic fashion, like Magnetar's ultramagnetic neutron stars with eruptions powerful enough to light up the universe. What made FRB 1211-02 even stranger was its behavior. Unlike the Lorimer burst's clean, one-and-done signal, this repeater's bursts were messy. Some were sharp, others were smeared or fragmented, as if something in its environment, like a swirling cloud of plasma, was distorting the signal on its way to us. This wasn't just a repeater, it was a cosmic lab offering clues about the turbulent spaces between galaxies. The implications were profound. If some FRBs could repeat, then their origins couldn't be purely cataclysmic. Suddenly, theories like flaring magnetars or pulsars on overdrive gained traction, while more exotic ideas like alien megastructures lost ground. It also meant astronomers could study FRBs not as fleeting anomalies, but as recurring events with patterns to decode. FRB 1211-02 became a Rosetta Stone in its own right, proving that the universe loves to defy our expectations. And here's the kicker. This repeater didn't just challenge assumptions, it opened a new observational frontier. By monitoring its bursts, scientists could probe the invisible matter between galaxies, test Einstein's theories, and even hunt for clues about dark energy. All because one stubborn signal refused to fade into silence. So the next time you hear about a mystery solved in astronomy, remember FRB 1211-02. It's a reminder that the universe's greatest puzzles often come with twists, and that sometimes the most revolutionary discoveries are the ones that keep talking back. But just when we thought we were starting to crack the code on fast radio bursts, the universe threw us another curveball, one closer to home than anyone expected. In April 2020, astronomers spotted something unprecedented, an FRB erupting from inside our own Milky Way galaxy. This wasn't a signal from billions of light-years away. It was in our cosmic backyard, coming from a known object called SGR 1935 plus 2154. And what made it even more jaw-dropping, this FRB wasn't just a burst. It was a full-blown fireworks show linked to a magnetar, one of the most volatile objects in the universe. For years, magnetars had been a leading candidate for FRB sources, but proof was elusive until now. SGR 1935 plus 2154 is a highly magnetic neutron star, spinning frenetically and occasionally unleashing violent flares. When it fired off a millisecond radio burst with energy levels matching distant FRBs, it was like catching a cosmic criminal red-handed. Finally, we had a smoking gun, a magnetar capable of producing FRB-like signals right here in our galaxy. But here's the twist. Instead of simplifying the FRB mystery, this discovery made it even messier. Why? Because while this galactic burst shared key traits with its deep space cousins, it was also noticeably weaker, thousands of times less energetic than the FRBs we detect from across the universe. That raised a glaring question. If magnetars are behind some FRBs, how do we explain the universe's most powerful bursts, which outshine this one by orders of magnitude? The plot thickened when scientists noticed something odd about the magnetar's environment. Unlike the chaotic dwarf galaxy hosting FRB 1211-02, this Milky Way magnetar sits in a relatively quiet region. Yet its burst still displayed bizarre features like rapid brightness changes and strange polarization, hinting that even local FRBs are shaped by unseen forces, perhaps dense magnetic fields or surrounding debris. And then there's the timing puzzle. SGR 1935 plus 2154's FRB coincided with a flare-up in X-rays and gamma rays, a combo never seen in distant FRBs. Does that mean extragalactic FRBs also emit high-energy light we're just not detecting? Or are there multiple FRB recipes, with magnetars serving only one flavor? This galactic FRB didn't hand us answers, it handed us a magnifying glass. It confirmed magnetars can produce FRB-like signals, but it also forced us to reconsider everything else. Maybe the universe's most powerful bursts come from supermagnetars with even stronger magnetic fields. Maybe they're born in extreme environments that turbocharge their energy. Or maybe, just maybe, we've only scratched the surface of what causes these cosmic enigmas. One thing's clear, the Milky Way's FRB didn't simplify the mystery. It proved that even when we think we're closing in on an answer, the universe has a way of opening new doors and leaving us with more questions than we started with. Now let's shift gears to something even more puzzling: patterns hidden within these cosmic signals. Fast radio bursts aren't just random blips in the void. Some of them, especially the repeaters, seem to follow mathematical rhythms, as if the universe is tapping out a code. This discovery has reignited one of astronomy's oldest debates. Are these patterns the work of nature or something else entirely? Take FRB 1211-02, the first known repeater. When scientists analyzed its bursts, they noticed something extraordinary. The signals weren't just repeating, they were doing so in cycles. Every 157 days, like clockwork, this cosmic beacon would fire off a cluster of bursts, then go silent again. That's not just odd, it's precise. In nature, such regularity usually points to an object spinning, orbiting, or pulsating with incredible consistency. Could this be a neutron star wobbling like a top in a binary system? Or is there something even stranger at play? Then there's FRB 1800-916, the repeater with a 16-day heartbeat. For 12 days, it's active, blasting out bursts. Then for 4 days, absolute silence. This isn't just random noise. It's a cadence so clean it feels almost engineered. Some researchers suggest it's tied to a precessing magnetar, its magnetic axis slowly wobbling as it spins. Others wonder if it's the result of a dense debris disk around the object, periodically blocking our view. But here's the kicker: no known natural process perfectly explains why these patterns are so crisp and repeatable. And then there are the numbers themselves. Certain FRBs exhibit dispersion, measures the delay in their signals caused by interstellar plasma, that align a little too neatly with mathematical constants. One study even pointed out that the dispersion of FRB 1211-02's bursts could be broken down into ratios eerily close to prime numbers. Coincidence, maybe, but when you combine that with the timing patterns, it's enough to make even the most skeptical scientist pause. Of course, the moment you mention patterns and radio signals, one word comes to mind: aliens. It's impossible to ignore the elephant in the room. After all, humans have used radio waves for communication for over a century. Could these bursts be some form of cosmic Morse code? Scientists are quick to temper that excitement. The energy required to produce FRBs across billions of light years is staggering, far beyond any conceivable technology. And nature, as we've seen, is full of surprises. Pulsars, for example, beam out perfectly timed radio pulses without any intelligence behind them. But here's where it gets fascinating. The debate over artificial versus natural origins isn't just sci-fi speculation, it's a real scientific tension. On one side, you have researchers hunting for even subtler patterns, hoping to crack a potential cosmic cipher. On the other, teams are building models to explain how magnetars or collapsing neutron stars could produce such precise timing naturally. The truth, we don't know yet. But every new repeating FRB with a weird rhythm adds another piece to the puzzle. So are these patterns nature's way of showing off, or is there something more profound at work? For now, the universe isn't giving up its secrets easily. But one thing's certain: the more we listen, the more these bursts seem less like cosmic static and more like a message waiting to be decoded. Now let's venture into one of the most speculative yet intriguing corners of the FRB mystery, their potential connection to dark matter. While most theories about these bursts focus on neutron stars or magnetars, a handful of scientists are asking a far more radical question. Could fast radio bursts be the fingerprints of dark matter itself? Dark matter is the universe's biggest ghost story. It makes up roughly 85% of all matter in the cosmos, yet it doesn't emit, absorb, or reflect light. We only know it exists because of its gravitational pull on galaxies. But what if dark matter isn't completely invisible? Some researchers propose that certain exotic forms of dark matter, like actions or primordial black holes, could interact in ways that produce bursts of radio waves. Imagine a dense clump of dark matter passing through a magnetic field, vibrating like a plucked string and releasing energy as an FRB. It's a wild idea, but in astrophysics, sometimes the wildest ideas lead to breakthroughs. One tantalizing theory suggests that FRBs could be the result of dark stars collapsing. These hypothetical objects, made entirely of dark matter, might implode under their own gravity, releasing a catastrophic burst of energy. If true, this would mean we're not just detecting cosmic accidents, we're glimpsing the death throes of something completely alien to ordinary matter. Another fringe idea involves dark photons, particles that could convert into radio waves under extreme conditions. If FRBs are the byproduct of such conversions, they'd be the first direct evidence of physics beyond the standard model. But here's the catch: there's no smoking gun. No FRB has ever been definitively tied to a region rich in dark matter, and the signals we've detected don't carry any unique signatures that scream exotic particle. Still, the lack of evidence hasn't dampened curiosity. In 2018, a team proposed that the strange afterglow of some FRBs might align with predictions of dark matter annihilation. Others point to the way certain bursts seem to cluster in regions where dark matter should be abundant, like the halos of distant galaxies. Are these coincidences or clues? Of course, the dark matter angle comes with huge caveats. Most FRBs fit neatly into existing astrophysical models without invoking unseen particles. And without direct proof, these theories remain in the realm of what if. But that's the beauty of FRBs. They're forcing us to question everything. Whether they're linked to dark matter or not, the mere possibility pushes the boundaries of what we think is possible. After all, the universe has a habit of being stranger than fiction. So while dark matter FRBs remain a long shot, they remind us how much we still don't understand. Every unexplained burst is an invitation to rethink the rules. And in the hunt for answers, sometimes the most outlandish ideas are the ones worth chasing. Now, let's turn our attention to another cosmic enigma that has often been mentioned in the same breath as fast radio bursts, the infamous WOW signal. Detected in 1977 by the Big Ear radio telescope in Ohio, this powerful, narrowband radio burst lasted for 72 seconds and appeared to originate from the constellation Sagittarius. What made it so unforgettable was its intensity and the fact that it fit the exact profile of what scientists expected an extraterrestrial signal to look like. Decades later, despite countless searches, nothing like it has ever been detected again, leaving the WOW signal as one of the most tantalizing mysteries in the search for extraterrestrial intelligence, or SETI. Fast radio bursts share a lot in common with the WOW signal. Both are fleeting, incredibly powerful, and seemingly one of a kind, at least until repeaters like FRB 121102 came along. But unlike the WOW signal, which was never observed again, some FRBs have been caught repeating, adding new layers to the puzzle. The similarity between these phenomena has reignited SETI curiosity. Could FRBs be another form of technosignature, a deliberate signal from an advanced civilization? The idea isn't as far-fetched as it sounds. An alien civilization might use focused beams of radio energy for communication or even propulsion. And if those beams happen to sweep past Earth, we'd detect them as incredibly brief but intense bursts, just like FRBs. This possibility gained serious traction in 2017 when Harvard researchers proposed that FRBs could be artificial in origin, possibly leakage from powerful interstellar light sails. Think about it, if an advanced species were propelling spacecraft using lasers or microwaves, some of that energy might escape into space, reaching us as millisecond-long flashes. Even more intriguing is the idea that repeating FRBs could be beacons, intentionally sent out to announce a civilization's presence. The fact that some bursts show complex patterns, like FRB 1809-16's precise 16-day cycle, only adds fuel to the speculation. Of course, the natural explanations for FRB's magnetars, neutron-star collisions, still hold more weight. But the mere possibility of an artificial origin has forced SETI to take another look. After all, if we're searching for intelligent life, we can't ignore signals that fit the criteria, even if they're also explainable by natural phenomena. The WOW signal taught us that sometimes the most promising detections are the ones we can't easily replicate. In that sense, FRBs are like the WOW signal on steroids, far more numerous but equally mysterious. So why does this comparison matter? Because it reminds us that the universe is full of surprises. Whether FRBs turn out to be cosmic accidents or deliberate messages, they've already done something remarkable. They've made us question, once again, whether we're truly alone. And in the search for answers, sometimes the most compelling clues are the ones that keep us guessing. Now, shifting our focus to another layer of the FRB mystery, let's talk about the secrets hidden in the polarization of these bursts. Polarization might sound like a technical term, but it's essentially the direction in which light waves vibrate as they travel through space. When FRB light is polarized, it's like seeing a cosmic fingerprint, one that reveals the intense environments these bursts pass through. Scientists have found that many FRBs show a high degree of polarization, particularly a type called circular polarization. This suggests the bursts are traveling through regions with incredibly strong magnetic fields. Think of it like a radio signal passing through a storm of magnetic chaos. The more twisted and scrambled the signal becomes, the fiercer the magnetic environment must be. Some FRBs even display what's known as Faraday rotation, where the polarization angle twists as the light moves through magnetized gas, further confirming the presence of extreme magnetic forces. So, what could create such conditions? One leading suspect is the vicinity of a black hole or a neutron star. Black holes, especially those with swirling accretion disks, generate some of the most intense magnetic fields in the universe. If an FRB passes near one, its polarized light would bear the scars of that encounter. Similarly, neutron stars, especially magnetars already prime candidates for FRB origins, have magnetic fields trillions of times stronger than Earth. A burst traveling through such a field would emerge heavily polarized, giving scientists a clue about its birthplace. But there's more. The polarization patterns in repeating FRBs sometimes change between bursts, hinting that their surroundings are dynamic. Perhaps a magnetar's crust shifting or a black hole's accretion disk fluctuating. This variability adds another piece to the puzzle, suggesting that FRBs aren't just one-off explosions but might be tied to ongoing cosmic upheavals. The study of FRB polarization has even bigger implications. By analyzing how these signals twist and turn, astronomers can map the magnetic landscapes of distant galaxies, shedding light on regions that would otherwise be invisible. It's like using FRBs as cosmic probes, revealing the hidden magnetic tapestry of the universe. So, while polarization might seem like a small detail, it's a powerful tool, one that's helping scientists peel back the layers of these enigmatic bursts and uncover the extreme forces shaping them. Whether it's the grip of a black hole or the fury of a magnetar, polarized light is whispering the secrets of the universe, one burst at a time. Now, stepping into another intriguing corner of the FRB mystery, let's untangle the puzzle of their rare but fascinating afterglows. Most fast radio bursts vanish in the blink of an eye, but a handful defy expectations by leaving behind a faint, lingering radio echo, like a cosmic fingerprint that refuses to fade. These afterglows aren't just curiosities, they're potential keys to unlocking what triggers these bursts in the first place. Take the case of FRB 121102, the first known repeater. Alongside its bursts, astronomers detected a persistent radio source, a dim but steady glow that outlasted the milliseconds-long explosions. At first glance, you might think it's just leftover energy, but the truth is far more complex. One leading theory suggests these afterglows could be shock waves from colossal cosmic collisions. Picture two neutron stars smashing together, releasing not just an FRB but a turbulent aftermath of hot debris and magnetic chaos. The resulting shock waves might glow faintly at radio wavelengths, lingering long after the initial burst fades, but here's where it gets contentious. Not all afterglows fit the collision narrative. Some seem tied to magnetars, neutron stars with earthquake-like crust fractures that unleash flares. In 2020, when the Milky Way's own magnetar SGR 1935 plus 2154 spat out an FRB, telescopes caught a flicker of radio emission lingering afterward. Was this a magnetar's bruise from the flare, or evidence of a recurring energy release like a cosmic wound slowly healing? The debate rages on because if magnetars can produce both FRBs and afterglows, it challenges the idea that all lingering emissions stem from violent crashes. Then there's the wild card, fast radio bursts with no afterglow at all. Why do some leave echoes while others vanish without a trace? It might come down to environment. FRBs erupting in dense, magnetized regions like near a black hole's accretion disk could ignite longer-lasting shock waves, while bursts in quieter cosmic neighborhoods might leave no trace. Or perhaps the afterglow is there, but too faint for our telescopes to catch. What makes these afterglows so valuable is their power to map the unseen. By studying their duration and brightness, astronomers can estimate the density and magnetism of the material they're plowing through, almost like using the afterglow as a flashlight to illuminate the murky corners of the universe. Every flicker adds a piece to the puzzle, whether it points to a magnetar's tantrum or the wreckage of a neutron star demolition derby. So while afterglows are rare, they're anything but silent. Each one whispers clues about the forces shaping FRBs, nudging us closer to answers. Are they cosmic crash sites, magnetar aftermaths, or something entirely unexpected? For now, the universe keeps this secret close, but with every new detection, we're learning to listen a little better. Now, shifting our gaze to the cosmic clockwork that shapes these bursts, let's explore how Einstein's theory of relativity bends the very fabric of time around fast radio bursts. Imagine an FRB racing toward us across billions of light years, a journey so vast that the expansion of the universe itself stretches and warps its signal like taffy pulled thin. This isn't science fiction. It's the real-world magic of time dilation, where gravity and the universe's growth conspire to slow down time itself from our perspective. Take FRB 20,220,610A, the most distant burst ever detected, hailing from a staggering 8 billion light-years away. By the time its signal reached Earth, the universe had stretched so much that its milliseconds-long chirp arrived slower and lower in pitch than when it began. Why picture space as an inflating balloon? As the balloon expands, dots on its surface move apart. Now, imagine a wave traveling between those dots. The stretching space elongates the wave, reddening its light and slowing its arrival. That's cosmological time dilation in action, and FRBs are some of the most precise cosmic stopwatches we have to measure it. But there's another layer, gravitational time dilation. If an FRB erupts near a supermassive black hole, a region where gravity warps spacetime like a bowling ball on a trampoline, its signal would climb out of that steep gravitational well, losing energy and further slowing from our viewpoint. Astronomers call this Shapiro delay, and it's why some FRBs arrive with tiny hiccups in their timing. These delays aren't glitches. They're breadcrumbs leading us to invisible mass hidden along the burst's path, from dark matter halos to lone black holes drifting between galaxies. Here's where it gets even wilder. Because FRBs traverse such vast distances, they let us test relativity on scales Einstein never could. In 2021, scientists compared the arrival times of different radio frequencies from FRB 190,520. High frequencies outpaced low ones by a hair, exactly as relativity predicts when signals plow through ionized gas in space. But a few bursts defied expectations, hinting at gaps in our models. Could unknown physics be at play, or is the universe's expansion accelerating faster than we thought? The irony is delicious. These fleeting bursts, over in milliseconds, are teaching us about time itself, how it stretches, twists, and reveals the universe's secrets. With each new FRB, we're not just mapping space, we're auditing cosmic time, one relativistic tick at a time. Now, let's turn our attention to another cosmic trick of the light gravitational lensing, and how it twists the signals of fast radio bursts into something even more mysterious. Picture this: an FRB travels across the universe, but instead of moving in a straight line, its path bends around a massive object like a galaxy or a black hole. This isn't just bending light, it's bending space itself, warping the burst signal in ways that reveal hidden corners of the cosmos. Gravitational lensing happens because massive objects curve spacetime around them, acting like a cosmic magnifying glass. When an FRB's radio waves pass near one of these objects, they don't just go around it, they split, creating multiple copies of the same signal arriving at slightly different times. Think of it like looking at a streetlight through a glass of water. The light bends, creating distorted reflections. With FRBs, those reflections can tell us what's hiding in the darkness between galaxies. Take FRB 180,924, detected in 2018. When astronomers traced its origin, they noticed something odd. Its signal seemed to flicker in a way that didn't match a single, clean burst. The culprit, a massive galaxy between us and the FRB, warping its signal like a funhouse mirror. By studying the delay between these echoes, scientists could map the invisible mass of that galaxy, including its dark matter halo, stuff we can't see but whose gravity leaves fingerprints on passing light. But here's where it gets even more fascinating. Some lensed FRBs don't just split, they brighten, as if the universe turned up the volume. That's because lensing doesn't just bend light, it amplifies it. In 2020, researchers observed an FRB whose signal was magnified by a foreground galaxy cluster, making it easier to detect despite its mind-boggling distance. This isn't just a lucky break, it's a tool. By studying these amplified bursts, astronomers can probe the distribution of dark matter in ways traditional telescopes can't. Yet lensing doesn't always play nice. Sometimes the distortions are so subtle they're almost invisible, hiding clues in the tiniest hiccups of an FRB signal. That's where next-generation telescopes come in. Projects like the Square Kilometre Array, set to launch in the coming years, will have the precision to catch these whispers of warped spacetime, turning every lensed FRB into a roadmap of the unseen universe. So, what does this all mean? FRBs aren't just flashes in the dark. They're cosmic messengers, and gravitational lensing is the decoder ring. Every warped signal, every delayed echo, is a clue pointing us toward the invisible scaffolding of the universe. And with each new burst, we're not just listening to the cosmos, we're seeing it bend. Now, let's shift gears to one of the most baffling fast radio bursts ever detected, FRB 190520. This repeater doesn't just behave strangely, it outright defies expectations, challenging everything we thought we knew about these cosmic signals. What makes it so unusual? Unlike most FRBs, which flash briefly and go silent, this one keeps chattering away, emitting a faint but steady stream of radio waves between its powerful bursts. It's like a radio station that never fully turns off, even when the main program isn't airing. This persistent emission is just the first clue that something's different here. When astronomers pinpointed FRB 1905-20's home, a small, unremarkable dwarf galaxy about 3 billion light-years away, they discovered another oddity. The environment around it is packed with dense, turbulent plasma, the kind you'd expect near a newborn star or a black hole's chaotic outskirts. Normally, FRBs pass through relatively calm interstellar space, but this one seems to be shouting through a cosmic storm, its signals scrambled by the thick soup of charged particles around it. The real puzzle, that plasma shouldn't exist where it is. Theories suggest repeating FRBs might originate from magnetars, highly magnetic neutron stars. But magnetars usually sit in cleaner environments, their emissions unclouded by such dense debris. So why is FRB 1905-20 drowning in this messy plasma? Some scientists speculate it's a young magnetar, freshly formed from a supernova and still surrounded by the chaotic wreckage of its birth. Others propose it's trapped in an unusual binary system, its companion star flooding the area with ionized gas. Then there's the burst pattern itself. While most repeaters fire off randomly, FRB 1905-20's bursts seem to cluster in time, as if it's active for a while before going quiet. This isn't just academic curiosity, it challenges the idea that all repeating FRBs operate the same way. Could there be subclasses of repeaters, each with its own quirks? The more we study oddballs like this, the clearer it becomes that FRBs might not fit into neat little boxes. What's next? FRB 1905-20 is a gift to researchers precisely because it breaks the rules. By unraveling its mysteries, why it chatters non-stop, why it's shrouded in plasma, we might uncover entirely new physics or stellar life cycles. Upcoming telescopes like the Next Generation Very Large Array will peer deeper into its turbulent home, searching for the engine behind this cosmic rebel. One thing's certain, the universe loves throwing curveballs, and FRB 1905-20 is a pitch we're still learning how to catch. Now, let's take a step into the realm of the truly mind-bending. Fast radio bursts don't just challenge our understanding of astrophysics, they've also sparked wild, speculative theories that flirt with the edges of quantum physics and even science fiction. Could these cosmic flashes be tied to phenomena like quantum spacetime foam or cosmic strings? It's a stretch, but the sheer weirdness of FRBs has scientists willing to entertain some far-out ideas. First, let's unpack quantum spacetime foam. This isn't some bubbly cosmic bath. It's a theoretical concept suggesting that at the tiniest scales, space itself might be churning with fleeting, microscopic fluctuations in the fabric of reality. Think of it like static on an old TV screen, but for the universe. Some researchers wonder if FRBs could be ripples or glitches in this quantum foam, emissions from these vanishingly small disturbances amplifying across cosmic distances. It's a radical idea, but if true, it would mean FRBs aren't just cosmic fireworks, they'd be whispers from the very foundation of spacetime. Then there's the cosmic string hypothesis. These are hypothetical, spaghetti-thin defects in the universe, left over from the Big Bang, thinner than an atom but staggeringly dense. If one vibrates or snaps, it could release a torrent of energy, potentially in the form of an FRB. Imagine plucking a guitar string so massive it spans galaxies, and the note it plays is a burst of radio waves. The math checks out, but here's the catch: no one's ever detected a cosmic string. There are ghosts in the equations, making this theory thrilling but unproven. Of course, this is where we hit the boundary between cutting-edge physics and science fiction. Quantum foam and cosmic string ideas are fascinating thought experiments, but they lack direct evidence. Mainstream astrophysics still leans toward magnetars or colliding neutron stars as the more plausible FRB sources. Yet, the very fact that such exotic theories are on the table speaks to how little we truly grasp about these signals. FRBs force us to ask, are we seeing the limits of known physics, or just the beginning of something entirely new? What's next? While these quantum-connected theories remain speculative, they're not dismissed outright. Future detectors like gravitational wave observatories or ultra-sensitive radio arrays might one day spot the fingerprints of space-time foam or cosmic strings. Until then, FRBs keep us humble, reminding us that the universe often reserves its most dazzling secrets for those willing to venture beyond the textbook. So, while we might not have aliens or quantum foam answers yet, the journey to solve these mysteries is just as electrifying as the bursts themselves. Now, let's turn our attention to another head-scratching quirk of fast radio bursts: the strange echoes that accompany some of them. Picture this: a single FRB hits our telescopes, but instead of one clean signal, we detect multiple blips arriving at slightly different times. It's as if the universe is playing a cosmic game of telephone, and scientists are racing to figure out why. One leading explanation points to interstellar scattering. As an FRB travels across the vastness of space, its radio waves don't always zip through unimpeded. They can bump into clouds of ionized gas or turbulent plasma, which act like cosmic prisms, bending and scattering the light. This creates a smearing effect where parts of the burst take slightly longer paths to reach us, resulting in those delayed echoes. Think of it like shouting into a canyon. Your voice bounces off the walls, creating reverberations. In this case, the walls are the chaotic soup of particles between galaxies, and the echoes are the FRB's radio waves taking scenic routes. But there's another tantalizing possibility: reflections off cosmic debris. Imagine an FRB blasting past a dense object like a black hole's accretion disk or a cluster of ancient stellar remnants. Some of its signal could ricochet off these structures, creating secondary pulses that arrive moments later. Astronomers call this multipath propagation, and it's not unlike how sunlight glints off a disco ball, sending light in multiple directions. If true, these echoes could act like cosmic sonar, revealing hidden objects lurking along the FRB's path, objects we'd otherwise never detect. Here's where it gets even weirder. Some FRB echoes aren't just delayed, they're also distorted, with certain frequencies arriving before others. This frequency-dependent delay hints at the environment the burst traveled through. For instance, if lower frequencies lag behind higher ones, it suggests the signal plowed through a region with lots of free electrons, like the halo of a galaxy. It's a bit like how red light bends less than blue light in a prism, and scientists can use these subtle clues to map the invisible scaffolding of the universe. Of course, not all echoes fit neatly into these boxes. A handful of FRBs show patterns so peculiar they defy easy explanation. Could there be entirely new physics at play, like warped space-time or exotic matter bending the signals? Or are we just missing a piece of the puzzle? For now, each echoed FRB is a breadcrumb trail leading us deeper into the unknown. One thing's certain: these cosmic echoes aren't just noise, they're messages etched into the bursts themselves, waiting to be decoded. And with every new detection, we get a little closer to understanding the universe's hidden symphony. Now, let's journey even further into the cosmic unknown with a record-shattering fast radio burst that rewrote the rules. In June of 2022, astronomers detected something extraordinary, an FRB so distant it felt like peering back in time. Designated FRB 2020-2610A, this burst came from a staggering 8 billion light-years away, making it the most far-flung FRB ever discovered. To put that into perspective, this signal began its journey when the universe was less than half its current age, long before Earth even existed. What makes this detection so groundbreaking isn't just the distance, it's what the burst reveals about the early cosmos. FRBs like this are cosmic time capsules. As they travel across the universe, their radio waves interact with the sparse matter between galaxies, leaving subtle fingerprints. By analyzing these distortions, scientists can map the conditions of the ancient universe. For example, the dispersion of FRB 2020-2610A's signal suggests it passed through more ionized gas than expected for its epoch. This hints that the early universe might have been clumpier than our models predicted, with pockets of matter that shouldn't have existed yet. It's like finding wrinkles in what we thought was a smooth cosmic blanket. But here's the real kicker. Detecting such an ancient FRB pushes our telescopes to their limits. At 8 billion light-years, the signal was incredibly faint, requiring ultra-sensitive instruments like the Australian Square Kilometre Array Pathfinder to catch it. The burst's brightness also defied expectations. Despite its mind-boggling distance, it packed as much energy as FRBs from much closer galaxies. This raises a tantalizing question: were the sources of early FRBs inherently more powerful, or did the young universe's environment amplify their signals? Either way, FRB 2020-2610 challenges our assumptions about how these bursts evolve across cosmic time. Perhaps most exciting is what this means for probing the universe's dark ages, the mysterious era before the first stars ignited. FRBs from this distance act like flashlights, illuminating the invisible gas that dominated the cosmos back then. If we can find more bursts this old, they could reveal how the universe transitioned from a dark, neutral fog to the star-filled tapestry we see today. Every distant FRB is a messenger from a forgotten chapter of cosmic history, and with each new detection, we're rewriting the story of how everything came to be. So while FRB 2020-2610 holds the distance record for now, it's almost certainly a preview of even deeper discoveries to come. The universe, it seems, still has plenty of secrets left to share. Now, let's shift our focus to another cosmic puzzle that's been stirring up debates among astronomers: fast blue optical transients, or FBOT for short. At first glance, these fleeting flashes of light seem to share some eerie similarities with fast radio bursts. But are they truly cousins in the cosmic family, or just celestial doppelgangers? FBOT are among the universe's most enigmatic optical bursts, appearing as sudden, intensely bright blue flashes in the night sky before vanishing just as quickly. Unlike FRBs, which are detected in radio waves, FBOT shine in visible light, often outshining entire galaxies for a brief moment. Yet both phenomena share a key trait: they're incredibly short-lived, lasting mere milliseconds to days. This raises the question, could they be different faces of the same underlying cosmic event? One of the most famous FBOT, nicknamed the Cow, was spotted in 2018. It flared up without warning, emitting a bizarre mix of light and radio waves before fading into obscurity. Intriguingly, some FRBs have been detected alongside similar optical counterparts, hinting at a possible connection. Scientists have proposed that both could stem from cataclysmic events, like the collapse of a massive star into a black hole or the collision of neutron stars. But here's where things get murky. While FRBs are thought to originate from highly magnetized environments like the vicinity of magnetars, FBOT often leave behind traces of expanding debris, suggesting a more chaotic, explosive origin. What's even more puzzling is the energy output. FRBs pack a concentrated punch in radio frequencies, whereas FBOT unleash a broader spectrum of light from X-rays to ultraviolet. This stark difference has led some researchers to argue that they're entirely separate phenomena, merely masquerading as kin due to their fleeting nature. Others, though, speculate that they could be different stages of the same event. Imagine FBOT as the fiery birth cry of a cosmic explosion, with FRBs as the distant radio echoes of its aftermath. The challenge in solving this riddle lies in the sheer rarity of both events. Capturing an FRB and an F-bot simultaneously is like finding two needles in a galactic haystack. But with advanced telescopes now scanning the skies around the clock, astronomers are inching closer to answers. Each new detection chips away at the mystery, revealing subtle clues about whether these bursts are cosmic relatives or mere coincidences. So, are FRBs and F-bot two sides of the same coin, or entirely different currencies in the universe's vast treasury of wonders? For now, the debate rages on, but one thing's certain. The more we learn about these transient phenomena, the more they blur the line between what we know and what we've yet to discover. And that's what makes them so thrilling to study. Now, let's peel back another layer of the FRB mystery, one that might seem mundane at first but has huge implications for cracking these cosmic codes. Imagine you're trying to listen to a faint whisper in a crowded room. The chatter around you makes it nearly impossible to pick out the exact words. That's essentially the challenge astronomers face with the so-called foreground problem when studying fast radio bursts. Here's the issue: when an FRB's signal travels across billions of light years to reach us, it doesn't zip through empty space. Instead, it passes through galaxies, clouds of gas, and other cosmic structures along the way. These intervening objects act like static on a radio, distorting the signal and muddying the data. For instance, a nearby galaxy's magnetic field might twist the FRB's polarized light, making it seem like the burst originated in a much more magnetized environment than it actually did. Or ionized gas from a foreground cluster could scatter the radio waves, smearing the signal's sharp edges and tricking telescopes into misjudging the burst's distance. This contamination isn't just a minor nuisance, it's a major roadblock. Pinpointing an FRB's true distance is crucial for understanding its energy output and origin. Take the famous Repeater FRB 121102. Early observations suggested it was embedded in an extreme environment, possibly near a supermassive black hole. But later studies revealed that some of those extreme traits might have been exaggerated by foreground interference. If we can't filter out these contaminating effects, we risk misreading the bursts entirely, like trying to solve a puzzle with half the pieces warped. The problem gets thornier with non-repeating FRBs. Since they fire just once, astronomers can't double-check their measurements with follow-up observations. A one-off burst might appear to come from a distant dwarf galaxy, but what if its signal was bent by a closer, invisible cloud of plasma? Without repeat detections, it's like judging a book by a single blurry page. Efforts to untangle this mess are underway. New algorithms can now model how foreground objects distort FRB signals, helping astronomers clean the data. Telescopes like the Square Kilometre Array, with its unprecedented sensitivity, aim to map these intervening structures in detail, turning noise into clarity. But for now, the foreground problem remains a stubborn fog in our cosmic window, one that keeps us from seeing FRBs as they truly are. So, the next time you hear about an FRB's mind-bending properties, remember, some of those quirks might not belong to the burst itself, but to the cosmic clutter in its path. And that's what makes separating the signal from the noise one of the trickiest and most vital steps in solving the FRB enigma. Now, let's shift our focus to one of the most baffling rhythmic patterns in the cosmos, FRB 180916, and its eerily precise 16.35-day cycle. Picture a cosmic lighthouse that flashes not randomly, but with the regularity of a finely tuned clock. That's exactly what astronomers observed when this repeating fast radio burst unveiled its secret rhythm, sparking a whirlwind of theories about what could possibly choreograph such perfect timing. First, let's unpack the discovery. Detected by the CHIME telescope in Canada, FRB 180916 didn't just repeat, it did so on a schedule. For roughly 4 days, it would fire off bursts like clockwork, then fall silent for 12 days before starting the cycle all over again. This wasn't a fluke. Over months of observations, the pattern held firm, ruling out coincidence and demanding a physical explanation. The precision was so striking that it felt almost engineered, yet nature has its own ways of creating order in chaos. So, what could explain this celestial metronome? One leading theory points to a precessing neutron star. Imagine a spinning top wobbling as it slows down. A neutron star's magnetic axis might similarly tilt over time, sweeping its beam of radio waves across space like a spotlight. If Earth lies in its path only during part of this wobble, we'd detect bursts in a predictable cycle. But here's the catch: the 16-day gap is unusually long for such a phenomenon, leaving some scientists skeptical. Another compelling idea involves a binary system, a neutron star locked in orbit with a massive companion, perhaps a B-type star shrouded in a dense disk of gas. As the neutron star plows through this disk periodically, the surrounding plasma could act as a trigger, igniting bursts only during specific orbital phases. This would neatly explain the active and silent periods, much like seasons on Earth. Yet, no such companion has been spotted near FRB 180,916 host galaxy, leaving this theory tantalizing but unproven. Then there's the wild card, magnetar quakes. Some suggest that fractures in a magnetar's crust could release energy in cycles, though no known model predicts a 16-day interval. Others wonder if the pattern is an illusion, a chance alignment of multiple bursters whose combined signals mimic periodicity. But with FRB 180,916 consistency, that seems less likely. What makes this mystery so gripping is its implications. If the cycle stems from orbital motion, studying it could reveal the hidden dance of compact objects. If it's precession, we're glimpsing the inner workings of neutron stars in unprecedented detail. Either way, FRB 180,916 isn't just a burst, it's a cosmic clock, ticking away clues to the universe's most extreme physics. As we keep listening, one thing's clear: this 16-day enigma is more than a curiosity. It's a key that might unlock the door to understanding not just FRBs, but the violent, beautiful mechanics of the cosmos itself. Now, let's turn our attention to the invisible fabric of the cosmos' interstellar plasma, and how fast radio bursts shine a light on its hidden secrets. Picture a signal traveling billions of light years through space, not just as a straightforward beam, but as a shimmering, flickering beacon. That's the effect of plasma, the ionized gas filling the vast voids between stars and galaxies, and it's one of the key players in shaping how we detect and interpret FRBs. When an FRB races through space, it doesn't travel through emptiness. Instead, it encounters this diffuse, electrified plasma, which acts like a cosmic lens, bending and scattering the radio waves. This phenomenon, called scintillation, is similar to how stars appear to twinkle when viewed through Earth's atmosphere. But in the case of FRBs, this flickering isn't just a visual quirk, it's a treasure trove of information. By studying these distortions, astronomers can map the distribution and density of plasma along the burst's path, uncovering structures that would otherwise remain invisible. Here's how it works. As the FRB signal passes through regions of varying plasma density, different frequencies of the burst arrive at slightly different times. This creates a telltale, smearing effect in the data, like a radio echo. The more turbulent the plasma, the more pronounced the smearing. By analyzing this pattern, scientists can reconstruct the environment the burst traveled through, almost like using sonar to map the ocean floor. For example, some FRBs show extreme scintillation, hinting at dense, magnetized plasma clouds near their sources, possibly remnants of supernova explosions or the chaotic surroundings of a magnetar. But the insights don't stop there. Plasma physics also helps explain why some FRBs appear brighter or fainter than expected. In regions where plasma is clumped together, it can act as a natural amplifier, focusing the radio waves like a magnifying glass. Conversely, areas with sparse plasma might let the signal pass through unscathed, offering a clean glimpse of the burst's original properties. This variability is why no two FRB detections are exactly alike. Each one carries the fingerprints of the unique plasma landscape it traversed. Perhaps the most exciting revelation is how scintillation can expose the large-scale structure of the universe. The cosmic web, the sprawling network of filaments and voids that defines the distribution of matter, is threaded with plasma. By tracking how FRBs scintillate across different distances, researchers can probe this web in unprecedented detail, even measuring the elusive, missing baryonic matter that's too diffuse to see with telescopes. So, the next time you hear about an FRB's flickering signal, remember, it's not just a burst, it's a messenger revealing the hidden architecture of the cosmos, one plasma ripple at a time. And with every new detection, we're piecing together a clearer picture of the universe's most enigmatic spaces. Now, here's a twist in the FRB mystery that's left astronomers scratching their heads. Some of these powerful bursts seem to come from nowhere. That's right, when scientists train their telescopes on the spot where an FRB erupted, they sometimes find nothing. No galaxy, no star cluster, just empty space. This is the missing host problem, and it's as puzzling as it sounds. Think of it like hearing a loud explosion in the distance, but when you rush to the scene, there's no crater, no debris, just silence. For FRB, the absence of a visible host galaxy raises big questions. If these bursts are born from cataclysmic events like neutron star collisions or magnetoflares, why can't we see their home? One leading theory suggests these FRBs might come from rogue neutron stars, cosmic nomads flung out of their galaxies by violent encounters, now drifting alone in the void. Without a galaxy's glow to overshadow them, their bursts could be the only clue to their existence. But there's another possibility. Some host galaxies might simply be too faint or too far away for current telescopes to spot. Imagine trying to see a single candle flame from thousands of miles away. It's nearly impossible unless you have the right tools. Similarly, telescopes like Hubble or even the James Webb Space Telescope might miss a dim, distant galaxy shrouded in cosmic dust. In fact, a few hostless FRBs later revealed faint, dwarf galaxies when observed with more sensitive instruments, proving that sometimes the universe hides its secrets in plain sight. Then there's the wild card. Could these FRBs be coming from regions so dense with gas and dust that they completely obscure their host galaxies? Picture a galactic neighborhood where thick clouds block every trace of light. Only the penetrating power of radio waves could slip through. This would mean the missing hosts aren't missing at all. They're just cloaked in cosmic camouflage. The implications are huge. If FRBs truly have no hosts, it challenges our understanding of how these bursts form. But if they're merely hidden, it pushes the limits of our observational technology. Either way, the missing host problem reminds us that the universe still holds cards close to its chest. With next-generation telescopes and sharper detection methods, we might soon uncover these ghostly galaxies or confirm that some FRBs really are cosmic drifters, lighting up the darkness with no home to call their own. One thing's certain, every hostless FRB is a puzzle waiting to be solved, and each discovery brings us closer to unraveling one of space's most persistent enigmas. Now let's shift gears and uncover how these mysterious bursts are actually helping us map the cosmos. Fast radio bursts aren't just cosmic oddities, they're powerful tools astronomers use to study the invisible scaffolding of the universe. Imagine FRBs as flashlights in a pitch-black forest. As their light travels billions of light years to reach us, it passes through clouds of ionized gas, magnetic fields, and even the faint threads of matter connecting galaxies. Each burst carries fingerprints of these structures, revealing secrets about the universe's web-like architecture. Take intergalactic space, for example. It's not entirely empty. Instead, it's filled with extremely thin ionized gas, so diffuse that traditional telescopes struggle to detect it. But when an FRB's signal passes through this gas, it slows down slightly, a phenomenon called dispersion. By measuring how much the signal stretches, scientists can calculate the density of this elusive material. It's like using a radar to map fog. The more the signal scatters, the thicker the fog must be. This technique has already helped close the gap on the universe's missing matter, the half of all atoms predicted by theory but never directly observed until FRBs illuminated the way. Then there's magnetism. Cosmic magnetic fields are notoriously hard to study, especially in the voids between galaxies. But FRB signals often arrive polarized, meaning their light waves vibrate in specific directions. When these waves twist as they traverse magnetized regions, they reveal the strength and structure of those fields. Picture rubbing a magnet against a sheet of paper covered with iron filings. The invisible force leaves behind visible patterns. Similarly, polarized FRBs expose the hidden magnetic tapestry woven through the cosmos. Perhaps the most striking use of FRBs is mapping the cosmic web, the vast filamentary network of matter that binds galaxies together. Simulations suggest this web exists, but its faintest strands evade direct detection. Here's where FRBs shine. By analyzing how their signals bend or delay as they cross different densities, astronomers can trace the web's contours. It's akin to echolocation. Just as bats use sound waves to navigate, scientists use FRBs to see the universe's skeleton, and the potential goes deeper. Some FRBs exhibit scintillation, flickering caused by scattering off turbulent plasma. This noise isn't a nuisance, it's a gold mine. By studying these fluctuations, researchers can probe the clumpiness of intergalactic gas, much like how twinkling starlight reveals Earth's atmospheric turbulence. What makes FRBs so revolutionary is their versatility. Unlike other cosmic probes limited to specific distances or conditions, FRBs work across the entire universe. From nearby galaxies to the edge of observable space, they encode information about every environment they traverse. With each new burst, we're not just solving a mystery, we're sketching a richer, more detailed map of the cosmos. So the next time you hear about an FRB, remember, these fleeting signals are more than enigmas. They're cosmic cartographers quietly charting the universe's hidden blueprint. Now let's tackle the ultimate question that lingers in the minds of scientists and enthusiasts alike. Are fast radio bursts natural cosmic events, or could they be something far more extraordinary? This debate isn't just about astronomy, it's about how we interpret the universe and our place within it. On one side, we have the weight of natural explanations backed by decades of astrophysical research. On the other, there's the tantalizing possibility that FRBs might be evidence of advanced extraterrestrial civilizations. Let's break down both sides of this cosmic coin. First, the natural explanations. The leading theories point to extreme astrophysical objects like magnetar's highly magnetic neutron stars capable of producing bursts of energy powerful enough to explain FRBs. We've even detected an FRB within our own galaxy linked to a magnetar, giving this theory strong credibility. Then there's the idea of colliding neutron stars or black holes, cosmic collisions so violent they could generate these fleeting, intense signals. These explanations fit neatly within our understanding of physics, and importantly, they follow Occam's razor, the principle that the simplest solution is often the correct one. But what about the other side of the argument? The notion that FRBs could be artificial isn't as far-fetched as it might seem at first glance. Some researchers, including those involved in the search for extraterrestrial intelligence, have speculated that highly advanced civilizations might use powerful beams of radio waves for communication or even propulsion. If an alien civilization wanted to send a signal across galaxies, a brief, high-energy burst like an FRB could be an efficient way to do it. This idea ties back to the Fermi paradox, the puzzling absence of detectable alien life despite the high probability it should exist. Could FRBs be the missing evidence we've been searching for? Then there are the oddities that keep the debate alive. Take FRB 121102, the first known repeater, which not only sends bursts in a predictable pattern but also originates from a dwarf galaxy, an unexpected location for such a powerful phenomenon. Some have wondered if these patterns could be intentional, though most scientists caution against jumping to conclusions. After all, nature is full of repeating phenomena, from pulsars to planetary orbits. So where does that leave us? While the idea of alien megastructures is undeniably fascinating, the scientific consensus leans heavily toward natural origins. The universe is vast and filled with extremes we're only beginning to understand. FRB, with their staggering energy and mysterious behavior, fit right into that category. But that doesn't mean we should dismiss the possibility entirely. Science thrives on curiosity, and the search for answers, whether they confirm our expectations or shatter them, is what drives discovery forward. In the end, FRBs remind us how much we still have to learn about the cosmos. Whether they're the products of magnetars, collisions, or something beyond our current comprehension, one thing is certain: they're pushing the boundaries of what we know. And that's the real beauty of these enigmatic signals. They challenge us to think bigger, dig deeper, and stay open to the extraordinary possibilities the universe might still have in store. Now, as we wrap up this journey through the cosmos, let's take a moment to reflect on the 25 baffling mysteries of fast radio bursts we've explored. From their mind-bending origins, whether neutron stars, colliding black holes, or even speculative alien technology, to their staggering energy output and their role as cosmic lighthouses illuminating the universe's hidden structure, FRBs have consistently defied easy explanation. They challenge our understanding of physics, force us to reconsider the boundaries of natural phenomena, and keep astronomers awake at night with their unpredictable behavior. Think about the implications. These fleeting signals, some traveling billions of light years to reach us, carry secrets about the universe's most extreme environments. They've revealed missing matter in the cosmic web, hinted at the violent lives of magnetars, and even sparked debates about the very nature of reality, with theories tying them to quantum space-time or dark matter. Yet, with every discovery, like the Milky Way's own homegrown FRB or the eerie 16-day cycle of FRB 180,916, we're reminded how much we still don't know. That's the thrill of FRBs. They're not just cosmic oddities, they're invitations to rethink what's possible. Whether you're drawn to the solid science behind magnetar flares or intrigued by the wilder notion of extraterrestrial engineering, these bursts remind us that the universe is far stranger and far more creative than we often give it credit for. So here's where you come in. After diving into these 25 mysteries, which theory resonates with you? Are FRBs the product of nature's most violent phenomena, or could they be something even more extraordinary? Drop your thoughts in the comments below. We'd love to hear your take on these cosmic enigmas. And if you're as captivated by the universe's unsolved puzzles as we are, don't miss out on more deep dives into space's greatest mysteries. Hit that subscribe button and tap the notification bell so you never miss an update. Who knows, the next big FRB discovery might be just around the corner, and you'll want a front row seat when it happens. Until then, keep looking up. The cosmos still has plenty of surprises in store.